Okay, great. So thank you. Thank you to the organizers for the invitation to speak here. Thanks, Ching, for the very kind introduction. And I think thanks also to the earlier speakers. It's been a really, really beautiful and inspiring collection of talks so far. I really enjoy the morning and the beginning of the afternoon. So this talk is going to be a little bit of a change of pace from the talks that we've seen so far. So the theme of the talk is really to try to take a step back and tell you about a few things that we've sort of encountered in trying to think about deep networks from a little bit of a more mathematical perspective. And the particular theme here is one of trying to understand how deep networks interact with low-dimensional structure in data. So we've seen a lot of talks so far on sort of diffusion models or generative models for image reconstruction, right? How we can do such an amazing job of capturing the structure in our target images with a diffusion model or with other generative models. We've also seen a couple of talks, especially Jeff's talk, Jung Cho's talk this morning, that allude to the fact that the success of these models can, at least to some extent, be attributed to their ability to capture structure in data, right? In Jeff's talk, we saw this manifold of small image patches, right, that are sort of well-structured, well-sized, and suited for learning. In Jung Cho's talk, we saw this very explicit manifold interpretation of how solving inverse problems with diffusion models works, right? That we're sort of walking along the manifold while enforcing our observation constraints. Okay, so this talk is going to be about deep learning with manifolds. This is a topic that just disappeared. All right. So we have a very difficult inverse problem. There we go. Okay, now we have more observations. Okay, so this is joint work with a few fantastic PhD students. I'm lucky to have amazing PhD students and former PhD students. And these folks, Sam Buchanan, Dar Gilboa, Tim Wong, these are really the folks who are responsible for this work, both at the technical level and also to some extent for the generation of the work, right? So around 3 or so years ago, they kind of took me aside and said, sparse linear inverse problems are great, blind deconvolution is great, but the world is changing. Maybe you should be working on deep learning. Maybe there's something in this sort of deep nonlinear neural networks. And so as we started to explore this space, coming to it from maybe a little bit more of a applied math or kind of high dimensional statistics perspective, the kind of questions that I wanted to ask are, what are the mathematical model problems for deep learning, right? When deep learning people think about their data sets or think about the problems that they would like to solve, how do they formalize them? And the reason that this is kind of a natural instinct for us, I think, was illustrated really nicely in some of the talks this morning, that if we can find the right kind of core formulation, well, maybe that can encompass a large number of applied problems. Also, if so, we can get insights that are kind of stackable, right? So for those of us who, sort of grew up around compressed sensing and sparse sampling, it's not just that the algorithms are interesting, but also that we kind of are learning things along the way, right? And one of the things that's been emphasized a lot through the day is this critical role for structure in solving inverse problems, right? I'm going to do a good job in high dimensions if my target is well structured. And maybe there's some more technical things. I'm going to do a good job if my measurement operator, maybe that's my MR device or something else, is interacting nicely with that structure, and so on and so forth. Okay, so those of us who are kind of more classical applied mathematicians, whether from statistics or controls or information theory, we tend to ask, what's a simple model problem? Okay, Now, one thing that we'll immediately notice about this deep learning field is that that's not how this field thinks at all, right? This is a field that's really driven by empirical results. And as we've seen in the talk so far, is really driven by this amazing ability for very complicated models trained on increasingly large data sets to capture structure that's hard to model analytically. Okay, so it's like a very data-driven field. At the same time, for those of us who like math, have a little bit of a theoretical bent, there's a tendency maybe to dismiss some of this, like, okay, the results are improving, but what are we learning? But actually, if you look across the sequence of papers, it's not just that performance is getting better. There are actually really fascinating intellectual insights that develop through this effort to push the performance with larger and larger models, right? And these are just a few of them that are familiar to all of us, right? If we have complex data, we're going to do better with a deeper model. At a more technical level, if we want to set up a deep model and have it train well, it's going to be really important that that deep network preserve the structure of features, right? Need to avoid exploding and vanishing gradients, make sure that things propagate well through my model. And then finally, probably the most fascinating one is that if you look at highly performant networks, often these are operating in a regime that classical statistics, even the kinds of intuitions that you would get from things like this, really say should not be effective, right? These are regimes where, at least in the kind of native parameterization of our network, we have a lot more parameters than we have data samples. Okay, and so there are some really interesting insights and kind of surprises here. Okay, so, as someone who likes mathematics and, maybe spends 50% of their research time trying to do mathematics, then the question is, well, what actually is a role for mathematical analysis here, right? Like, what mathematical problems should we be studying, and what can it give us, since the field is already doing so well? And so these are just a few personal answers to that question. One personal issue that kind of bothers me a lot, especially coming originally from a background in computer vision, is what I'll call uniformity. That in a lot of situations, we have a data generating process that can generate data with various parameters, and we would really like to make sure that our method works for all choices of those parameters, right? So if I take my pointer here and I start translating it around, we'd really like to make sure that our recognition system doesn't fail when I move it to a new location, right? So I have, some set of images of this pointer. I want to make sure that I succeed uniformly over that set. Maybe a kind of more challenging, but structurally similar version of that is questions about robustness, right? So I want to make sure that if I make some kind of supposedly imperceptible perturbation to my image, I don't drastically change the classification result. And as we all know, these are axes along which it's really easy to embarrass well-performing deep learning models, right? If you go looking for adversarial transformations, even adversarial translations for some models, you can find them. If you look for adversarial perturbations in some norm, again, you can find them. So, these are situations where we would like some kind of a for-all statement. And, it's kind of natural to think about a for-all statement in terms of trying to understand whether we've uniformly captured the structure of the data, right? So it feels like it needs a little bit of math. Or not. Okay. So there we go. And then maybe the third issue, which I think has really been recurrent in the talks so far in this meeting, is the issue of how the network should reflect the structure of data, right? And that's both at the level of what are the right network elements and simply how much network, how much data do I need, right? When we talk about generative modeling, of data. This is all about making sure that we correctly capture the structure of data. Okay, and so, as we tried to take some baby steps into this field, we found ourselves really zeroing in on this issue of data structure. Okay, so in the first part of this talk, what I'd like to do is I'd like to talk about some really kind of cartoonish model problems around learning with low-dimensional structure. So we're going to ask, how do deep networks learn? When can we guarantee that they learn over low-dimensional manifolds? Okay, so I have a high-dimensional data space. Data have low-dimensional structure. When do I correctly capture that structure? Okay, so in light of some of the talks that we've seen already, maybe I don't need to spend too much effort justifying a manifold assumption. But it's worth noting that there are both situations where this is applicable as an approximation. If I think about all of these pictures of different types of dogs, well, these are low dimensional in the sense that they don't fill image space, right? They're much lower dimensional compared to the ambient dimension. Not super intrinsically low dimensional, maybe about 26 dimensional, 43 dimensional, but still not filling the whole space. Also, there are some phenomena that we encounter in visual data that actually give us legitimate low-dimensional manifold structure in the mathematical sense, right? And one good example of this is image transformations, right? As I move this around, this is going to cut out some maybe 6-dimensional manifold in my image space. Okay, so we can get low-dimensional structure from this kind of statistical concentration around lower dimensional sets. We can get it from the physics of data generation. There are some problems where we run into a really clearly defined low-dimensional structure that is actually directly connected to the physics of the data. This is just a small example of this. This is coming from a collaboration with some astrophysicists. This is Zabi and Zusamarka at Columbia. They're part of this scientific collaborative that is looking for gravitational waves, right? So these are sort of gravitational signatures of events in outer space. For our purposes, we don't need to get too much into the details of how these are actually generated physically, just to say that the way that this data is generated is I have large objects that bang into each other in outer space. These would be things like black holes and neutron stars. And when this happens, they create this kind of ripple in space and time. And that's actually the gravitational wave. And so what people have done is they've built these giant and kind of absurdly sensitive instruments, which are basically several mile-long interferometers that are actually able to be sensitive to this kind of tiny perturbation in the fabric of space-time. Okay, so that's kind of the data. Now, what does this have to do with low-dimensional structure? Well, this is an example of how I can get low-dimensional structure in data from the physics of data generation, right? It turns out that these physical systems are actually relatively simple. If I think about this pair of black holes that are circling each other up here, this can be described by a relatively small number of parameters. Probably the most important ones are the masses of the two black holes, right? As they become more massive, they sort of circle each other faster and faster. And so, maybe I get a more oscillatory signature. And this is just looking at a bunch of clean sort of simulated examples of this. And then this is what they look like if we apply PCA and put them in a zero-dimensional space. Okay, so and this is what they look like in a three-dimensional space. Okay, so there's some kind of strong low dimensionality. Okay, so in general, we're trying to capture low dimensionality. It may be this kind of approximate low dimensionality where the data don't fill the space. it may be this more structural low dimensionality where there's a kind of generative process with a few parameters. Okay, and so what I'd like to do for the next kind of small part of the talk is to extract this kind of very cartoonish toy problem from that and talk a little bit about how we can study that problem mathematically. So the cartoonish toy problem that I'm going to extract is this thing that we call a multiple manifold problem. Just means that I have data in high dimensional space, like we've been talking about all day, that are concentrated on or near two low dimensional manifolds. Okay, so I have two low dimensional sets. Here it's the hedgehogs and the hairbrushes, right? And what I'm trying to do is to learn a classifier that correctly labels those two sets. Okay, so I have my two manifolds. We'll call them M plus and M minus. You show me labeled data. So these are xi, yi's. Here the xi's are the data points. The yi's are the labels. And what I want to do is I want to learn a classifier, which for us is going to be a deep neural network, that puts the right sign on every point from each of the two manifolds. Okay, so if it's on the hedgehog manifold, it gives it a positive number. If it's on the hairbrush manifold, it gives it a negative number. Okay, so a couple of things that we can notice here. One is that in some sense, this problem is a lot simpler than all of the problems that we've seen discussed so far today, right? Here we're dealing with clean data that are living on these two low dimensional structures. So it's like a very, it's kind of a toy problem. On the other hand, what we're asking of our learning method is a little bit strong in the sense that we would like it to correctly classify every point on.
Big question.
Yeah, please.
What would the label be in this particular case? What is y?
What is y? Okay, good. Yeah, so y is going to tell me which class I belong to. So in our setup, y is +1 if I'm the first class, -1 if I'm the second class.
It is what you want to learn, because I was really confused about it.
Okay, yeah, no, I appreciate the question. Yeah, feel free if there are other questions about. Let's see. Is this because the computer is sleeping, or is it because of the connection between the two? The laptop is sleeping. Okay. No. Okay. Yeah. I mean, we can sort of move on through and just bring it back every time. But yeah. Okay. While we're sort of paused there, any other questions about the setup? Okay. So if I try to think about this as, sort of a math problem, as a technical problem, then there are pretty clearly a few parameters that are going to tell me how easy or difficult this instance of the problem is. Right? It's going to be harder, meaning that I'll probably need more data and more network if the manifolds are higher dimensional. It's going to be harder if the manifolds are closer together. So dimension is going to play a role. The separation between the manifolds here, this is like a nearest point distance, is going to play a role. Also, the problem could become harder if the manifolds are highly curved. So here, this kappa, when it shows up in the results, is sort of an extrinsic curvature of the manifolds, telling me how much they're curving in the ambient space. And then finally, in the technical analysis, there's going to be one more parameter down here, which we'll call the Clover number, which we'll try to disambiguate a little bit later.
Quick question.
Yeah, please.
That in fact the manifolds are separate. You're assuming that.
We are assuming that.
They're not touching each other.
They're not touching each other. Yeah. And that's a good question. So
Delta is always greater than 0.
delta is always greater than 0. If one is interested in that situation where they do touch each other, then there's sort of enough under the hood here that you could extract a result about it. But of course, where they touch each other, you can't really guarantee anything.
Right.
Okay, yeah, good. Okay, but yeah, delta is greater than 0. Okay, and that's probably not the worst of it. So the worst of it is right here. So at least in the work that I'm going to talk about today, we're going to do this for the very simple case where these two manifolds are one-dimensional. Okay, so each of them is a curve in the high-dimensional space. Kind of similar to the previous comment, if you wanted a result for higher dimension, there's probably enough there to do it, but today we'll be talking about little d equals 1. Okay, so our two manifolds are really two curves. And as we'll see, there's, sometimes it happens that you find that you've written, some number of pages and spent some number of late nights and, still only have a result for d equals 1. Okay, so this is probably the most important restriction of the technical results that I'm going to tell you about, is here we're doing the one-dimensional case. Okay, now I mentioned this kind of last parameter here, something that I called a clover number. This is turning out to be important for technical reasons. So this clover number is, at an intuitive level, capturing the number of times that my manifold can loop back to the vicinity of a given point. Okay, so if I think about a clover, right, it's kind of loopy in space. So you can see here in this example, I have a point x, and I come back in the vicinity of that point 1, 2, 3, 4 times. So in general, this is going to be bigger if my manifolds tend to be self-similar. For example, for my 1 here, my 1 is approximately rotationally symmetric, so it sort of loops back to a given point twice. My 4 is not rotationally symmetric, and so it loops back only once. Okay, so this sort of clover number object is capturing how loopy my manifolds are. And it's kind of interesting to ask why that plays a role. The intuition is that as I tend to return to the same point many times, the numerical problem of kind of sorting out what goes on along the manifold becomes less and less well-conditioned. So if I have this structure where I'm entering and exiting a given neighborhood many, many times, that's going to be a harder problem. I'm going to need a little bit more network to figure out what's going on there. Okay, but that's our sort of last parameter here. It's so-called clover number. Okay, so in any case, this is sort of the setup. I can see at the rate we're going, we're probably not going to talk too much about the application side of this. For the application side of this, we're actually using networks that have modules that are sort of structured based on optimization. So we're following a lot of the discussion earlier today where we sort of bake structure of problems into networks. For theory here, I'm going to think about a very generic neural network. So my generic neural network is just going to be a fully connected multi-layer perceptron. Okay, so just this big box. It's going to have depth, big L, so that's the depth of the network. It's going to have width, little n, and I'm going to train it on big N data samples. And the kind of question that one would like to ask here is, well, okay, how do the resources that I require, that means the depth, the width, and the number of samples, depend on the complexity of the data distribution, right? So what's the relationship between big L, little n, and big N, and the properties of the geometric properties of the problem? And I think that, as we've sort of mentioned, it turns out that the mathematical analysis of these problems is challenging, right? There are some limitations to what we can prove with current technology. But I think that the style of this question is an interesting one, and I think it's really thematically related to the discussion earlier this morning. Even as we're talking about what's the right representation for the data. Should I use patches? Should I use the whole images? Well, okay, this is really a question about how the complexity of the data distribution relates to the resources that I have available to solve the problem. So, I think that if we wanted to look for directions where we might hope for further theoretical development, these kind of resource trade-offs, I think, are an interesting one. Okay. Now, why is it hard? Well, the reason that it's hard is if I want to prove a generalization guarantee, right? If I want to prove that I can learn a network that correctly labels not only the available data, but future samples from the same distribution, right? Sort of label everything on the manifolds. Then I have a question that sort of bridges geometry, optimization, and probability, right? Optimization because I need to know what happens when I train this network with something like gradient descent. Okay, so eventually questions about the success of deep learning methods mathematically are questions about the solutions of optimization problems. Of course, in contrast to the kind of results that we usually prove about optimizers, usually we like to prove that they're convergent to a critical point, maybe bound the suboptimality as a function of iteration. Here, I actually need to know that we're convergent to a minimizer that is good, right, in this particular sense. Okay, so that's a question about optimization. So here's an objective function. This objective function is just the square loss. Don't worry about the fact that it's written like an integral. That's just a sum over the training data. And what we're trying to do is to reproduce the observed labels. Okay, so we want to know, does gradient descent correctly label the manifolds? Okay, so why is this hard? Well, this is hard because I have a deep network. Each time I add another layer, now I'm adding another collection of variables of optimization. And those are interacting in this kind of complex nonlinear fashion with everything that came before. In particular, there's this kind of symmetry structure to this problem, where if I change the names of my intermediate features, I don't change the output of the network, right? So if I have a good solution over here, now I permute the features, I have another good solution over here, another one over here, another one over here, right? So this is always going to be a non-convex problem. And non-convexity in general is challenging. I have a sort of personally preferred approach to reasoning about non-convexity in high dimensions. And that's to try to think through the symmetry structure of the problem. So if I take something like learning a good data representation, so I want to learn 1, 2, 3, 4, n building blocks that can well represent a collection of data, say make them sparse, that becomes a non-convex problem. It's non-convex for the same reason, because if I change the names of my dictionary elements, I don't actually change their representation capacity. So I have lots of equivalent solutions in this in the space. And it turns out for these kind of simpler or more classical problems, these are things like dictionary learning, sparse deconvolution, it's actually possible to mathematically map out the geometry of this non-convex problem, figure out where the minimizers should be, and in some situations actually prove that the minimizers are in the right place. And Ching in particular is a pioneer in this kind of work. So a lot of the interesting contributions he played a very, very large role in. This works really, really well for shallow models. So if I have a model with implicitly one hidden layer, I can do a pretty good job of figuring out where the minimizer should be. The problem is that we have complicated data distributions. We're going to need deeper networks. And there we have this kind of compound symmetry structure that we may not really have the technology to reason about. Ching is trying really hard to change that, but it takes time. So what we're doing in this work is instead of trying to map out the geometry of the parameter space, we're going to follow some smart people in theoretical machine learning and say, instead of thinking about this neural network as a collection of parameters, I'm going to think about it as an input-output relationship. Okay, so in this representation, the kind of neurons in the network are just this big soup that helps me in realizing a particular input-output relationship. And if I try to think in that way, then it's really natural to ask, if I have pairs of data points, say I have an x and an x prime, and I want to understand, okay, how easy is it for me to change the output at x as opposed to the output at x prime, right? So how easy or hard is it to independently adjust these two outputs? Well, the kind of natural way of measuring that is through this object called the neural tangent kernel. This is something that we learned about from this paper of Jaco and collaborators. This is really widely used in the field. And again, the kind of intuition from this input-output perspective is that this is the inner product of the gradient of network output with respect to parameters evaluated at x with that evaluated at x prime. So again, if this is big, x and x prime tend to train together. If it's small, x and x prime tend to train separately. So you kind of like it to be big when you put in xx and small when you put in xx prime. Okay, so this again is a very natural object in sort of thinking about the input-output relationship. Says, okay, to what extent can I simultaneously adjust network outputs at different points while making small changes to the parameters? And the kind of trick here, which connects to some of the earlier discussion on overparameterization, is that if my kind of soup is rich enough, if my network is big enough, then I can bring back my laptop. All right. And let's try to get that full screen. Okay, if my soup is rich enough, then I can actually get a lot of work done in terms of the input-output relationship before this thing changes too much. So at a technical level, that becomes a very useful trick for sort of proving results, is that I can sort of treat this thing as if it's not changing too rapidly during training. Okay, and this object actually has a really natural connection to training in the sense that if I think about my objective function and I think about how the fitting error, so this zeta t is, I'm thinking about a continuous gradient descent. So I have my parameters, theta t. These are starting at some random starting point. They're flowing according to the gradient flow. If I think about how the error evolves under gradient descent, well, if I collect this theta object for all points x and x prime, I can think about this one as a big matrix, right? Just two entries, x and x prime, so it's indexed by data and data. Then the time derivative of my fitting error is the negative product of that matrix with the current fitting error. So I get this pretty simple dynamical system, right? Just a first-order differential equation where the change in the error is the result of pushing the error through this theta matrix. Okay, so the kind of utility of this is we started with a really complicated nonlinear problem, and now we're trying to study it through this very simple linear dynamical system. Okay, and so, for the students, if you have a little bit of background in control or dynamical systems, you sort of know that how quickly this one decays is going to depend on whether it's aligned with directions where this theta is big, right? Because over here I have the negative of the time derivative, right? So if zeta is aligned with directions where theta is big, then we're going to get fast decay. If it's aligned with directions where theta is small, we're going to get slow decay. And what that actually turns into when you study it is it sort of turns into high frequencies and low frequencies. These networks are really good at learning low frequency functions. They're not as good at learning high frequency functions. So sort of the higher frequency of the function you need to learn, the more network you're going to need. So that's sort of two intuitions for this theta object. Again, one is at a point level, measuring how well I can adjust network output at 2 points. And then if I think about it as a big matrix, it's sort of telling me what are the directions that are easy to learn. Okay, and so then the question is, well, what are the directions that are easy to learn? So this is a kind of visualization of this theta as a function of 2 data points. So I have a learning problem over the sphere. I have fixed 1 point x here. And now I think about what happens as I change the other point. In other words, how easy or hard is it for those 2 points to train together? And so up here is basically theta as a function of that other point. You can see that it's pretty close to rotationally symmetric. And it's really a function of the angle between x and the other point that I put in x prime. So as you might intuitively expect, points that are close together tend to go together when I perform gradient descent. Okay, and so do I want that to happen? Do I not want that to happen? How local do I want this thing to be? Well, that's going to depend a lot on the geometry of my data, right? If I have 2 points from the same manifold, I want them to go together because I want to generalize. If I have 2 points from different manifolds, I kind of want them to go separately because I want to put different labels on those 2 points. And it turns out that the depth of my network is actually a resource that helps me to accomplish that. In the sense that, so here I'm going to look at this theta object as a function of depth for increasing depth. So this is a shallow network. Now as I increase the depth, you can see that it becomes pointier and pointier, right? More like a pointy hat. And so intuitively speaking, this sharpening is part of what allows deep networks to adjust to complicated geometry, right? The deeper my network gets, the better I am at treating points as separate and giving them independent labels. Okay, so bigger network means sharper theta. So intuitively speaking, at least in this kind of theory setup, we want our depth to reflect geometry, right? We kind of want our depth to reflect the separation between the separation between the 2 manifolds. We need our network to be sensitive enough that we can put different labels on the 2 of them. Okay, then the other resources that we have in the problem, we have the width of the network, right? How kind of rich is our input-output soup? And we also have the number of data points. And in this setup, width is kind of playing a statistical role. It's sort of telling me how, if I start at a random initialization, how regular is the behavior of gradient descent? Does it take some very predictable trajectory? Will it take some kind of crazier trajectory? How confident can I be in its success? And here, as width gets bigger, we can be more confident. And so, under the hood, we won't go into the kind of technical details, but under the hood, the task that you kind of have to achieve mathematically is you have to control how the randomness from this random initialization propagates through the network. So that's kind of an interesting sequential probability problem. Okay, so that's sort of, for those who are really specialists, there are some sharp estimates here. There's some bounds on feature propagation. But again, the intuition here is that depth is a kind of fitting resource. Deeper networks fit more complicated geometries. Width is a kind of statistical resource. Wider networks can be expected to behave more regularly when we train them. And then finally, if I want to think about how much data I need, well, I kind of need to bring back this picture, right? This picture is telling me something about the sensitivity of the network output as a function of the distance between my data points. And we said for distinguishing between the two manifolds, we wanted it to be sharp, right? Because we want different points to train separately. For generalization, for labeling the points that lie in between, we actually want it to be not too sharp because we want it to be such that if I train this point, this one also ends up carrying the same label. So you can think about this as defining a kind of aperture. And you want your aperture to be small enough to classify correctly, but big enough to generalize. And so turning that around, the amount of data that you need is going to be a function of how wide that aperture is. OK, so these are sort of the three resource trade-offs that show up in this kind of analysis. You know, again, depth plays this role as a fitting resource. Set depth based on problem complexity. Then the number of samples sort of follows as a consequence of that depth, as a consequence of how sharp this kernel associated with the network is. OK, so you know, at this point, we've been going kind of fast, I realize, especially for the, you know, for the amount that's going on under the hood. But I hope that, you know, at least we've conveyed a few of these intuitions. If we wanted to put this together into some kind of a theorem, so this is the structure of the result. Basically, what it says is if I set the depth to be big enough relative to the structure of the data distribution, in particular, you know, if you care about the details, this is polynomial in 1 over delta in the inverse separation. And then we're going to set the width and the number of samples to be polynomial in the depth. Then what you can prove with this kind of analysis is you can prove that actually gradient descent does the correct thing. So we correctly classify every point on the two manifolds. OK, so I think what I hope to convey is a little bit of the intuition behind this. If you're a specialist, there are a couple of novelties here. One is just that this is an end-to-end generalization guarantee with low-dimensional structure. Two is that there's an important role for depth here. So really, to fit more complicated geometries, we need deeper networks. And the depth plays a critical role in the proof. OK, so that's for sort of the theory side. I can see that I have 2 minutes. So that's probably well beyond or far too little to talk about this sort of second half, which is actually, with this as intuition, how do we specialize these networks to solve scientific problems? So this I'll be more than happy to talk about offline. The high-level idea is that in a lot of these problems, we have relatively limited positive data. So if I think about this gravitational wave problem, we have only a handful of true real data detections. We have a lot of negative data. We have a lot of noise. And so one sort of needs hybrid training methods that are good in that scenario. And one also needs to build in a little bit of the structure of the data into the structure of the network. And so kind of like some of the talks that we've seen earlier in the day, here we're actually using properties of the manifolds in our network construction. In particular, we're sort of driving networks by unrolled optimization. You can leverage some geometric intuitions to sort of say how much network you need. So that's kind of a helpful bit there. There's a little bit of diffusion model feel to the whole thing in the sense that if you really want it to scale well to higher dimensions, then it's important to use a multi-scale method, which applies different levels of smoothing. So there's sort of a role for smoothing or injected noise or multi-scale. OK, so this is just kind of a funny version of this from computer vision where we're trying to get dimension-efficient navigation of image transformation manifolds. Again, the kind of theme is building the structure of problems into the structure of the network, which folks have discussed quite well earlier in today's symposium. Okay, so with that, thank you for the questions along the way and for for being here for the talk. Again, high-level message is trying to perform end-to-end analyses of learning with low-dimensional structure. There are a lot of directions for future work. I think as a sort of theory theme, this is a really interesting one. Also, as we've seen throughout the day, we always do better when we build in prior knowledge about the structure of the manifolds. And I think with that, I will cut off and just thank the students and welcome any questions. Thanks.
Thank you so much. Does anybody have any questions?
I see a couple in the back there.
Yeah, I'm coming to the back.
A slide about end-to-end guarantee slide. Is it a generalization bound?
It's a generalization guarantee in the sense that we have a really simple problem here, and then we prove something about as strong as you can prove about that simple problem. The thing that we prove is that you actually correctly label every point on both of the manifolds, including ones that you haven't seen before. So that's a guarantee of generalization.
So what is it deterministic?
Is it deterministic? No, this is all with high probability. And the high probability, yeah, I omitted that from the slide, but it's with high probability in both the data and the random initial network. So those are sort of the two sources of randomness.
Yeah, got it. Thanks.
Thanks.
Thanks for sharing. And I noticed that one of the conclusions is we need more data and wider network to enhance the performance. And there's a trade-off in data and the size of the network. So my question is, I noticed that you use the empirical risk minimization as a loss function. Mm-hmm. And is it still works, the conclusion still works in other forms of the loss functions or strategies? For example, the IRM, the environment risk minimization, and some strategies like densely sampling the checkpoints of the models and smoothing the parameters. And that's because they are important techniques in generalization problem. Mm-hmm. And in this problem, we have limited data and always want to be data efficient. So, yeah.
Yeah, so first of all, thanks for the question. I think it's a really good question. And so I think we can sort of separate. So first of all of the things that you described are good ideas, right? The use of invariant risk minimization, smoothing, even other loss functions besides the squared error, right? Like all of these things can help. The theorem that we have here is specific to this setup. So if you say right now you want me to write a theorem, then it's for this one. I think that my feeling is that it wouldn't be too difficult to generalize the result first to other losses, and also encompassing some of the things that you described, like invariant risk minimization, various sort of analytical forms of data augmentation. I think it's mostly technical to do this, and I think there's probably enough there. But I certainly don't have a result written down. So, but yeah, it's a good question.
Oh, thank you.
And of course, in the practical side of the work, we're pulling all of the tricks. So yeah, of course you want to do those kinds of things in practice.
We'll take one last question here.
Hi, John. Thanks for the nice talk. So
thanks.
Can you say anything about the representation learning? So whether the depths will make the features more linearly separable of the resources? So currently it's the fitting to the labels.
Yeah, so I think that's a really good question, and of course that's one that is very aligned with your work, and I think it's important. So you're sort of asking, what do we know about how the representations learn and how the problem becomes separable through training, right?
Right.
Both
so
in terms
if you
of,
have a linear classifier.
Well, right, both in terms of depth and training time, and so. In that depth training time graph, the theory results here provide a pretty comprehensive characterization of how features propagate at time 0, and then how you can leverage that to learn. But the theory here doesn't tell you how the features actually evolve over time. What we see sort of empirically, okay, so theoretically at time 0, there's this like predictable evolution of the feature geometry, right? There's sort of nominal evolution, which is under the hood here, right? So that's very clearly characterized. Now, what we see empirically with training over time is that the features do become more separable with training. So and the way that that reflects in the objects that were on the screen is that that kind of sharp, rotationally symmetric thing becomes more adapted to the data distribution. So it's like more elongated along individual classes and sort of sharp in the directions between classes, which is kind of what you would like. So,
thanks.
Yeah, thanks.
Okay, thank you so much. And that will bring us to our last speaker.